Thevenin analysis is useful for many reasons. As we saw before, is the idea is you have some complicated circuit, you can replace it with just a single voltage source in series with a single resistor, and then you can analyze what happens as you place different loads onto that circuit, and you can see what happens very quickly instead of having to solve a complicated circuit over and over again. But there's another use for it that's actually going to give us a really interesting and important result in many applications. What we're going to do is we're going to try to see is, well, how can we maximize the amount of power that is going to be going through this resistor? So we know power, there's different ways of calculating it. Let's say for now I times V. So you might say, okay, well, how is this going to work? Well, we can also rewrite that as I squared R. So it seems like the greater your current is, the more your power is going to be. However, your current is based on your resistance as well, in terms of the voltage across it. And if you have a big resistor, you're going to have a small current, so you'd have small power. But if you have a small resistor, you're going to have a small voltage, so small power. So the thing is, if you have too big of a resistor, it's not going to give you that much power. And if you have too small of a resistor, it's not going to give you too much power. So we're going to try to, how do you find the sweet spot of just the right perfect resistance that will get the maximum power there? Now, there are many reasons why you might want to do this, but one that is maybe the easiest application of it is, let's suppose that this load over here is a speaker. Well, if you're going to have a speaker, you want to have the maximum power going to that speaker so that you can produce the most, the loudest sound, right? So, I mean, obviously you can turn the volume down and so on, but you want to have the most power so you have the most capability on that speaker. So that's what we like to see. How is this going to work? Well, if I go ahead and say, well, let's call that VR over here, the voltage across the resistor, by a voltage divider, VR is going to be the total voltage, V Thevenin, times the resistor we're at over the sum of their two resistors. And if I want the power on that resistor, it'd be the voltage of the resistor divided by the value of the resistor, RL. And so we're going to go ahead and take this big mess here, and we're going to square that, divide by RL. It simplifies a little bit here, V Thevenin squared times, so it would have been RL squared, but one cancels, and we have RL plus R Thevenin here squared. And keep in mind that V Thevenin and R Thevenin, they are just constants here. That was based on the original system here. We're just trying to see what load RL is our only variable for this problem. So what we're going to do is we're going to take the derivative of this expression with respect to R Thevenin, right? You want to find maximum and minimum from calculus. You take the derivative set equal to 0. Now this is a bit of a pain here, so I'm just going to kind of do it quickly, and you don't really need to worry too much about the details. So the V Thevenin squared is constant, bring it along. Then we're going to have to do the quotient rule here. So the derivative of the top times the bottom minus the top times the derivative of the bottom. And for that, we're really using chain rule there. And then all over the bottom squared. It was already squared, so squared squared makes it the fourth power. And we can even factor out one of these RL plus R Thevenins on top, and it will end up canceling out here. So then on top, we're going to have RL plus R Thevenin minus 2RL over this part, and then we still have the V Thevenin squared here. And so if we want this whole thing to be 0, that's only going to happen when the numerator is 0, which is when R Thevenin minus RL is 0. So for that, we need RL to be R Thevenin. And so this gives us our nice result here that if you want to maximize the power, you need the load resistance to equal the Thevenin resistance of your circuit. Now, if you actually look a little bit more detail, especially the other derivation in the book, you're really going to see that it's the absolute value of R Thevenin. Now, majority of the cases we're looking at, this doesn't really matter because R Thevenin is positive already. But if your R Thevenin was negative, you need to have the positive value for a couple of reasons here. One reason is it wouldn't actually make sense to make your load have a negative resistance. Remember that you can't actually build a resistor with negative resistance. That doesn't make any sense. The whole negative R Thevenin is from a mathematical model. Secondly, if you imagine that you have a voltage source and you have, say, a negative 5 ohm resistance for your R Thevenin and a positive 5 ohm, right? They're going to add up to 0, and it's going to make it, in some sense, infinite current going through this circuit. So that's, maximum power in that case is going off to infinity. But in the case where R Thevenin is positive, doesn't really matter, absolute value or not, it's the same answer. And then you're going to get a finite actual maximum power. Now, if you actually take this value and you plug it into the formula for the power, then that means that the max power you can ever get is going to be V Thevenin squared times, well, RL is the same as R Thevenin, over RL is the same as R Thevenin, plus RL is the same as R Thevenin squared. So you're going to get 2 R Thevenin squared there. And then we'd have V Thevenin squared over 4, one of the R Thevenins cancel, over 4 R Thevenin. So that gives you the maximum power you can have on a load resistor. Now, for anyone that's actually worked with electronics, you may have heard of something called impedance matching. That's basically what we're doing there. Impedance is something we will cover later on. It's basically resistance when you look at things in the right perspective. And so, again, if you want to get max power, you need to match the resistances or match the impedances.